Okay, welcome everyone. We will continue our discussions in this course looking at different kinds of classifiers. We just finished max margin classifiers and support vector machines as an example for that. And by the way, one side note that I wanted to make is SVMs with slacks are also called soft margin classifiers. If you see that word somewhere else, I think you just have to know that they are the same thing. SVM with slacks are called soft margin classifiers. Now we will go on to another classes of classifiers or function approximators called neural networks. Now neural networks are the today's go-to choice for classification, regression and all kinds of machine learning tasks, basically the distribution estimation or empirical risk minimization tasks. Now neural networks are versatile in the sense that they can approximate any function. We will see that formally in a while. There is this very powerful theorem called universal approximation theorem. We saw in our earlier discussions that the choice of the hypothesis class that we make is critical when we are solving the problem. Right? Now the one suggestion was to choose from the family of functions that are expressive enough. Now expressivity depends, can be defined in multiple ways, and one way of defining it is how good can it approximate the underlying function or underlying distribution, whatever way you want to put it. We already saw one universal approximator, which was Gaussian mixture models in terms of density estimators, but we saw that the algorithm or the iterative algorithm that is used to estimate the parameters may get stuck in local optima, which we do not want. Now, and that is from a probabilistic standpoint. From a ERM standpoint, one good choice for universal approximators are these class of functions called neural networks. Okay, so we will look at neural networks. There are multiple improvisations that have been made on a simple neural network. We will look at a few iterations of it. We will start from what is called as a perceptron, and then we will go to multi-layer perceptron, which is also called a feed-forward neural network. Then we will look at convolutional neural networks and recurrent neural networks, and of course the transformer, which is the current golden standard for machine learning. Okay. Now what is a neural network? So we still have the same problem of empirical risk minimization, same and by the way, as we have been seeing in this course, these hypothesis functions are independent of the fact whether you are solving a supervised problem or an unsupervised problem, because ultimately you are estimating distributions. We all know that, right? Now h theta of x is a neural network. So we all have seen, so let's define the data first. So let's say that x is in RD and y is in R for convenience. So h theta of x, we know that W transpose x is a linear decision boundary or a linear function. Let's say that we make it pass through a nonlinearity sigma, where this sigma can be the usual sigmoid that we have seen in the case of logistic regression or a logistic classifier. Now let's say that I take another weight matrix or weight vector W2 and multiply that multiply the outcome of this logistic sigmoid with another weight. Okay. Now this I make sure that this also passes through another sigmoid and so on. So now this becomes a composite function. So this thing is a composition or composite function comprising alternating linear and non-linearities. Right. So what we are doing is take the data, use a linear matrix and make it pass through a linear transformation, and then apply a non-linearity. You get another vector, and then pass it through another linear transformation, and then there is nonlinearity and keep stacking it. So this is called a neural network. This class of function is called a neural network. Now this sort of operation, okay, which is a linear transformation of data, is often referred to as a perceptron. Of course, there is a, you can have a nonlinearity. I mean, this nonlinearity can be the sign of this, decide based on the sign of W transpose X, right. So what is it basically doing is you are taking every dimension of data and scaling it with a particular scalar, or rather weighting it with a particular scalar, and that is why people notionally use W to denote the parameters, weights. So weighing each of the data dimensions, and then deciding based on a linear combination of different dimensions of different features or dimensions of data, right. So this is called a perceptron, and this idea of perceptron was first proposed in 1960s. So this is not a new idea at all. So this has been around, okay. Now people thought that this has vague connections with the way neurons fire. I am sure that neuroscientists do not agree with that, but there is vaguely, the thing is, neurons fire based on the weights of the features or the different kinds of measurement it does. I mean, vaguely people say that, but again there is no proof, so to speak, on this. But anyway, for us it's a mathematical function. So this is called a single layer or a perceptron, where you take a linear combination of data and decide based on the sign of it. So earlier people used to learn a perceptron. So what do you mean by learning a perceptron? It is finding out this W, not based on ERM, but based on an algorithm called perceptron learning algorithm, where the idea is very simple. Now suppose you are given a data set, okay, initialize with a particular W, okay, and take a data point and see whether the given data point is correctly classified or not correctly classified. If it's correctly classified, leave W and move to the next point. If it's not correctly classified, then you change your W by adding that particular data point. So please note that the dimension of W and the data point are same, because the inner product has to be between the vectors of same data points. You understood the algorithm, right? If it makes a mistake, then add that particular data point. So basically there is a decision boundary. If it makes a mistake, then tilt the decision boundary, which is, and the tilt is given by the magnitude of this particular data point. Okay, keep doing it and keep iterating over data. So there is a nice theorem that would show that if the data is linearly separable, this particular algorithm converges in finite number of steps. I think this will be done in tutorials. So it's a classical algorithm. This is called the perceptron learning algorithm. Okay, you understood the algorithm, right? So the WT plus 1 is WT plus XT, where XT is the tth data point if it makes a mistake. Okay, and that plus can be minus XT, depending upon whether it has come up. I mean, the decision is based on the sign. If it's above, then it's plus, and if it's below, then it's minus. What can be shown is if the data is linearly separable, then this particular algorithm converges in finite step, which will be done in tutorials. Please have a look at it. So this is perceptron learning algorithm. See, however, this perceptron is limited only to linear separability, and also it does not approximate all functions. So people moved away from perceptron, and then they came up with this idea called a multi-layer perceptron. MLP is also called a feed forward neural network, or fully connected neural network, as it is called. Okay. So what is the idea? So here it was W transpose X decide based on the sign. In a multi-layer perceptron, you start with some W1. Okay, so this is W1 times X. Okay, so instead of having a sign, so you have a sigma. Now if W1, okay, let's do that once. So let's say that X is in RD and Y is in RK. the most general setting. Now here W1 is a matrix of size. So this is let's write it as W1 itself. So this is D by 1 and this should be L1 by D, correct? Yeah, X is D by 1 and if W1 is L1 by D, and the sigma that we do is element wise, then this will be of dimensions, it is an L1 length vector, correct. Now I will have another W2 which is a matrix. Now W2 is a matrix of dimensions R L2 cross L1, right. So we get a L2 dimensional vector, okay, and then I will do another element wise nonlinearity. Okay, then let us say that we have another W3 here and W3 can be R L2 cross K, right, so that you finally get a H. So here theta is W1 and W2 and W3. Is this all right? This is how you construct a neural network. So this is a 3-layer neural network. But I've heard about deep neural networks, right? A number of layers that you have. Every W is called a layer, okay, and number of W's you have is called the depth of the neural network. Okay, so this is the most general case. So suppose you want your output to be for a classification problem, then you have to have a softmax after this W3. You understand? So it will become a k length one hot vector. And if you are solving a regression problem, you stop here at W3 and so on. Okay, so sigma here is element wise nonlinearity. See, one example of this can be sigma of t is 1 by 1 plus e power minus. This is one example of a sigmoid, and I will see multiple examples as we go later further in the course. Any questions on this, the construction of a neural network? I mean, the number of elements in all these W's are called the parameters. You have here, how many parameters do we have? L1 times D times L2 times plus L2 times L1 plus L2 times K, correct? So these many number of parameters is what we have. This is a multi-layer perceptron or a feed forward neural network or a fully connected neural network and so on. Why is it called a fully connected neural network? We will get to know that in a while, okay? Any questions on this? Yeah.
So it effectively captures the nonlinear mean of the distribution.
Did not make any of such statements. It is just a composite function of data, that's it, which involves linearity and nonlinear transformations. I did not say what does it effectively capture or anything. You can't say anything about it, we know what it is, right? It is just a hypothesis function. When we do ERM, we are minimizing the empirical risk, that's it. We should stop there. And we have every theory that comes up, right? We have the bias variance decomposition and we know how the error distributes and so on. So yeah, so it's a mathematical construct. What is more interesting is the theorem that I'm just going to talk about in a while. Yeah, but do you understand the mathematical construct of what a deep neural network is? This is effectively what is actually driving today's AI, okay? Yeah. I told you, right? This is one example. Oh, you mean every layer it can be, yes, it can be different in every layers. But typically it is chosen to be the same for convenience, okay? People have empirically found out that having different nonlinearities at different layers does not lead to gains in terms of performance. Yeah, should be k cross L2, right? Yeah, because finally we need a k dimensional vector. Thanks. Anything else? Okay, so let's move on now. See, why this particular form, right? I mean, this seems arbitrary, isn't it? So you have some linear transformation of data, then non-linearity, then linear transformation. Why? I mean, why should this be so powerful? Is because of this particular theorem, okay, which is called, this came in 1980s. This theorem is called universal approximation theorem. I just state it without the proof, okay, but let's write that down. So there is a theorem called universal approximation theorem. It says let X be a compact subset of Rn, can say Rd also, Rn is fine, and let's say C of X denote the space of all continuous functions. Continuous functions f from X to R. I am doing it by assuming that R, I mean the domain or range is R. It can be generalized to Rk as well. So then let sigma be a function from R to R such that is bounded, continuous or differentiable, and goes to 0, not -1. Asymptotically goes to 1 and 0 at both ends. So this is called an activation function. Okay. Now you can choose anything. It doesn't matter how it behaves in between. And the example that we just gave here has that property, right? One end it goes to 1, the other end goes to 0. Okay. This is a function this way. Then for any given target function, f that is there in the space of continuous functions and a threshold epsilon greater than 0, there exists an MLP with a single hidden layer with n neurons such that, by the way, I didn't define what a neuron is. So if you look at this is a matrix, right? If you take one of the columns of this matrix, what's happening is it's multiplying or scaling each of the feature dimensions with W, right? And then taking a sum of all of it, right? Which is W transpose X kind of operation. And there are how many of them here? L1 of such things here. So every W transpose X operation is called a neuron. This thing is called a neural network because you can write it that way, right? So here this I wrote it in the vectorized form. Write it as scalars, start from d-dimensional space, and then there is one neuron that would take one column of W and multiply it with all X. So write it as a neuron. There is another neuron that takes the second column of W1 and multiplies and scales and so on. There are multiple neurons and there is a network of all these neurons, and that's why the name neural network. Okay. So now here we are saying there exists an MLP with a hidden layer with one hidden layer, okay, just say instead of a hidden layer, say a single hidden layer with n neurons, such that the network's output f of x, or we will write it as h theta, h of x is given by 1 through n. We have some beta I times sigma of w transpose x plus some bias, okay, p, satisfies the condition that the supremum of the difference between this subbounded by epsilon for all x, where beta and w are parameters. See, this is why neural networks are powerful. So, what is this theorem saying? It is saying that you take any continuous function, okay, you can choose a beta and w. So, what is this? This is actually a single hidden layer neural network. Why? Look at this. This is w transpose x operation, there is nonlinearity and there is another w here. I mean, I can actually write it as, just to be consistent with our notations, I can write this as w2 and here w1, that is also fine. Yeah. So, this is a single hidden layer neural network. I mean, this thing, so this is called a hidden layer because the output is hidden from the input, right. So, the x is hidden from w2, that is why it is called a hidden layer. So, it is basically a neural network with one layer. Now, this theorem says that any continuous function can be approximated to arbitrary closeness, choose any epsilon, okay, with a single hidden layer neural network by choosing this w1 and w2. Now, please note that this theorem is not guaranteeing that any learning algorithm will get us to that w1 and w2, and it is not even telling us how many neurons should be there in the hidden layer. In fact, yeah, the summation should be over. Yeah, I mean, I wrote it in the vectorized forms, right? Hold on. Huh? No, it's just okay, I'll write it this way, it's fine. And it's all vectors, right? It's fine, but I'll have to, no, I have to somehow bring this in. Let me tell you. So, this w1, so w1 is a R L1 cross D vector and matrix, and w2 is R, yeah. So, we have output is 1, right? Yeah, this is correct. We are assuming that the domain is R here, you see, this is R. So, if it is R, the output has to be in R. So, the dimensions match now, they do, right. W1 is x is R, x is in RD. So, let us say x is in RD, if it is in RD then d by 1, W1 is L1 by D, and this has to be L2 cross, not L1, it should be, the output should be one dimensional. Let us match the dimensions now. So, there should be n layers in the hidden, no, the hidden layer, right. The first layer has D, and then you have W2, the first dimension of W has to be D, right. This is, let us write it down. So, this is R D by 1. So, this should be D by N, right, and this should be, we get an n dimensional vector, this should be n by 1, no. See, I am assuming that my output is one dimensional. Oh, this is W2, sorry. So, this should be, just matching this, hold on. So this is W1, W12 should be d by n, so you get an n dimensional vector, it should be n by d. Should I put a transpose here? This is n by d, this is n by d, so you have n neurons in the hidden layer, correct, and this should be 1 by n, correct, yeah, should be 1 by n, yeah, this is W2, correct, yeah. Now you have a neural network that has n neurons in the hidden layer, okay, and this theorem tells you that you can approximate any function to arbitrary closeness by this sort of a function. And if, I mean, as I said, it is not telling you how many neurons should be there in the hidden layer, neither it is guaranteeing that a learning algorithm like ERM will take you to those W1 and W2 that will make this difference bounded by epsilon. It is an existential proof, it is simply saying that you can find a function of that sort. Does it make sense? Now the question is, while this theorem tells you that all you need is a single hidden layer neural network, why are we looking at deeper neural networks? Today we have deeper neural networks, right? We do not have shallow and wide neural networks. We have we do not have yeah, this is deep and this is shallow, this is wide and narrow, yeah. So so we do not have shallow and wide neural networks, we have deep and narrow neural networks, no. Okay, let me write that. So this is depth and this is what? This is deep versus shallow, correct? And this is you want to call it wide and narrow, this direction. So what we have is deep and narrow neural networks, not shallow and wide neural networks. Why? Not because of that reason, it is purely because of the computational convenience. See, what people have found out is that if you want to approximate naturally occurring functions with the neural networks with limited width, then you need a lot of neurons in single layer. Are you people aware of this algorithm called fast Fourier transform? Do you know what the idea there is? The idea is actually this. So the computations that you do in one layer, so to speak, right? Basically, when you have composite functions, okay, you can approximate a complex function by having multiple layers of compositions is what you can show with lesser number of parameters. The same idea that is used in a fast Fourier transform, FFT kind of algorithms is what the idea is. However, theoretically speaking, people have demonstrated that whatever results you can obtain with a deeper neural network can be obtained using a shallow neural network as well, just that the number of neurons in the particular hidden layers have to be increased, okay. Come again? There is no theorem, this is all empirical, because the theorem only tells you that all you need is a single hidden layer. These are only empirical observations. And by the way, do you know the number of parameters that are used in today's neural networks? They are of orders of billions, yeah. So I also tell you, I mean, in a couple of classes I will tell you the today's neural networks, how is the, and by the way, the particular functional form that is used for this neural network is referred to as architecture. So this is a 3 layer architecture neural network and so on, right. See, the architecture that is used in today's neural network, we will see that as we move on in the class, but yeah, so that is the idea, yeah. Good question. The question, that's nomenclature. So the question is, if you call this a 3-layer neural network, then the one that is used in universal approximation theorem has to be a 2-layer. It is a 2-layer neural network with single hidden layer. This is a 3-layer neural network with 2 hidden layers. This is just to save my face, right? So I can actually call it a 2 neural network, depends upon nomenclature, that is it, yeah, good point. Okay, so let us move on. So now we will use deep neural networks, right. See, one thing that is to be seen is how do we perform an ERM on this. So finally we will have to start with a loss function and then calculate the empirical risk and then find out what the find out an algorithm to find these parameters, right. Now how do we do this is the question. We do it using gradient descent, okay. So let us look at ERM on neural networks. We will stop here and continue in the next lecture.